So I'm going to give you a little preview of some of the software, well, a little bit about the kits first, just to sort of set the stage for the ReproSeq workflow, and then describe a lot of work that we've been doing over several versions of Unruh Porter software development. So I'd like to add this slide just to give you a sense of, so where we're actually selling ReproSeq across the globe. We have a global reach, and I think what it really speaks to is the talented R&D scientists that I work with developing ReproSeq. It really is quite an approachable workflow. And it allows our customers to bring NGS into their labs worldwide. And as Alain was suggesting with some of the talks later, you can sort of think of it like a gateway drug to other applications on NGS. So it really sort of helps demystify some of the daunting aspects of next generation sequencing, and I think ReproSeq is a great platform to start your journey on next generation sequencing. So ReproSeq is a complete solution, and what it is aneuploidy detection by low-pass genome sequencing. And so it's dialed in to accept fairly low inputs from 1 to 10 cells. And within this workflow are the kits for library preparation, which is also includes the extraction and the barcoding for multiplexing on the various chips. Then templating takes place on the chef, and finally sequencing and analysis in Unruh Porter. So as Alain alluded to, it's rapid. It can be done in under 10 hours for the lowest throughput, up to 13 for 96 samples. It's flexible, and we're constantly improving the software for reliable detection of mosaicism and small event calling, which I'll talk about with the majority of this talk. And it's simple, so it's a plug-and-play workflow. And before I go on, I think it's worth sort of orienting ourselves on what low-pass genome sequencing actually is. And I like to think of it as whole genome sequencing on a diet. So it's essentially, for what people are familiar with WGS is, it takes a large number of reads, approximately 360 million, to cover the entire genome at an adequate depth, the genotype. But here we're not interested in calling SNVs or indels, but we're looking only at large chromosomal and subchromosomal CNVs. And in that case, you don't need to sequence to such the depth, so you can be much lower at less than 0.01x coverage, or approximately 100,000 reads. And one of the aspects of what we're doing with this application is copy number calling, but not running a reference in each run, but using a baseline to do the copy number calling. So, as you would think with all molecular techniques, there's bias comes in many sources. There's the library prep. We use a whole genome application. There's the sequencing itself and the GC content of various regions of the genome. And then there's the aligners that align the reads to the genome, which is impacted by read length, but also repetitive regions in the genome. And so when we're using our hidden Markov models here for copy number calling, the baseline is used to overcome these biases. And so the reads in your sample are compared to a normal control, and then corrections are made for under overrepresentation. So it's really about the baseline. And there's no need to, as I mentioned, no need to run a control in each time, and it helps correct for any of these GC content effects or any other bias. So, and what's also important with our software, I think is worth pointing out, is that we provide baselines, but you can actually use your own normals to create a baseline in Unruh Porter. So just touching quickly on the chips, I encourage everybody to come down to our booth because we have a great video that walks through a lot of how you set up the chef run and the instrument, and you can see a chip and see the actual instruments. The chef and the S5 are both on our booth, but it's worth noting that we are supporting 3 chips for the ReproSeq workflow: the 510, which supports 16 samples per run; the 520, which supports 24, and scales up to the 530 or 96 samples. So here's the 2 instruments that I mentioned, the chef and the S5, and just to give you a sense of where the time is spent on the workflow and sort of how it scales, going from 16 to to 96 here. The library prep scales from 3 hours to 4.5, depending on the number of samples, whereas we have a fixed time for the template preparation. And this portion here in dark blue is actually on the Chef instrument, so automated. So this is the only manual step here in light blue. And then gray indicates the sequencing run times here. This includes signal processing and base calling. So it scales from anywhere from an hour and a quarter up to 2.5 hours. And then that data is then automatically uploaded to Unruh Porter for analysis, with taking up to an hour for 96 samples to be processed. And we just want to sort of benchmark ourselves against one of our competitors, which is the Illumina VeriSeq. And as you can see, even when we scale to 96, we're quite competitive in terms of the hands-on time compared to the offering from, formerly of Illumina, now Vitrolife. It's comparable to what they do for 24 and reasonably close and actually faster for the same number of samples, and it scales nicely to 96 and doesn't add significantly to the total turnaround time. So I'm going to dive into some of the development we've been doing on the Unruh Porter software. This comes in two flavors. You can upload your data to the cloud, a free cloud version, or there's local server options. And when we first launched these kits, the S5 kits, a couple years back now, we were on version 5.4, and at that time we introduced mosaicism calling. We have a gender masking feature, which I'll show. And then we, based on customer feedback, improved our plots and introduced smoothing. And subsequent to that, we went through version 5.6 into 5.10. And now we have opened up some parameters so we can allow customers to increase the sensitivity of the calling through something called the transition penalty, and I'll talk about that some more. And then we've introduced smaller baseline tile sizes also to help with small event calling. And then we now have a filter, the expected normal ploidy buffer filter, which will filter events around normal ploidy to hopefully eliminate many putative false positive calls around normal ploidy. So here's what the plots used to look like in the genome view. It was this read cloud of jittered plots, and then you can see here a loss, and then gain shown in red, and then gains in blue, and this is without smoothing. So this can be user determined, so you can still opt for this view in Ion Porter. But a lot of the feedback that we're receiving is people actually prefer the smooth view, is you can differentiate the calls off of normal ploidy here much more cleanly. So this is now the default Ion Porter workflow with smoothing. And then this gender masking features come from requests from parts of the world where they're actively trying to prevent sex selection. So in this case, the report would come back with no reads shown in this genome view, and if you follow the arrow up, this sample would be the symbols for the sex symbols would be removed. It would just say sex chromosome normal here. Instead of the symbol for a male. So it's the same sample here, just with the gender masked. And if it was abnormal, it would state that it was an abnormal copy number for one of the sex chromosomes. And then this is the mosaicism calling, where it's an integer or decimal calling, not a full ploidy change. And we're using here a mixture sample, DNA mixture sample of 45 megabases on, is that chromosome 9? Maybe I can't see. So when we launched, this was the work that we did on non-mosaic events. So we did cell sorts and looked, made a large number of libraries, either looking at 45 or 48 megabase events on either 9 or 13, and then smaller sub-chromosomal events on 21 and 17. And as you can see here, we're doing quite well in terms of sensitivity and specificity for both for these 5 cell inputs. So, as I mentioned, like when we got to 5.6, we introduced this parameter, the transition penalty, and shown here are the default workflows. So high sensitivity is -3, medium is -8, and low is -5. And so going into a smaller negative number actually increases the sensitivity, or allows the algorithm to make a ploidy change. It is exactly what the name suggests. It lowers the penalty for the algorithm to change ploidy states. And just to give you a sense of what that does, you can see that here's this 7.9 megabase deletion here. It's visible on the plot, but not called by the software. So in using the high sensitivity workflow at a transition penalty of -3, it wasn't called. But when we lower the transition penalty in a custom sensitivity workflow to -2, this event is now called. It's hard to sort of make out, but the red dot is over that small event there. And so another aspect of the software that we worked on was the expected normal ploidy buffer. This helps with the detection of mosaic events. So there's a limit of precision for mosaic calls around normal ploidy, and there's a potential for false positives. So this ploidy buffer allows the filtering of these events, and the default is plus or minus 20% around the normal ploidy. But this can be user configured and set to based on your own internal testing. So just to give you a sense of how these two things might work in concert, in the past, and this is actually how we just came about working with R&D to introduce these parameters. Is we had these samples that were we made these mosaic samples that were subchromosomal, and as you can sort of see in the plot here, hopefully, what the algorithm was doing was wasn't making a complete ploidy jump across, and it was trying to smooth this over. So what happens is the ploidy is actually called at 1.8, even though it's a 40% segmental mixture. So we increased the sensitivity here to, using a transition penalty of -2.33, and what you can see is now the event is clearly separated from normal ploidy in a distinct fashion, and it's called at ploidy 1.65, which is close to the 40% the expected 40% of this mixture. But what maybe you can't make out as easily, but there's a whole lot of other calls happening around normal ploidy. Is the colored bars, and so this is noise around 2n. So how they work in concert is, so if you had the high sensitivity workflow and added the expected normal ploidy buffer, it actually filters the actual event out now because it was called at 1.8 or 20%. So it's filtered by that buffer. But now when we add the custom sensitivity workflow plus the expected normal ploidy buffer, you get the call, and all the noise around 2n is filtered out. So another aspect of improving sensitivities for subchromosomal events is the smaller tile size baseline. So basically this is just the bins across the genome that we bucket the reads in. And so at default it's 2 megabases, and with the new baselines that we provide, we now provide a 1 megabase tile size baseline and a half megabase. But this again can be user configured. So this is an example of the effect here. So looking at this 4.5 megabase deletion on chromosome 1, it's even at a transition penalty of -2, so a custom sensitivity. So increasing the sensitivity, but at a 2 meg baseline tile size, it's not even really isn't distinguishable there. But when we keep the high, actually we lowered the sensitivity back to just high sensitivity, but then did a half megabase tile size, and the event gets called and separated. And this is just a blue fuse plot from Illumina from the same sample. So I worked with some customers to collect data to sort of understand on a variety of samples what our customers are using in the field and their settings, and what event sizes they're calling. And with the high sensitivity workflow, again, this is transition penalty -3 and a 2 meg tile size baseline, it's capable of calling down to 6 to 8 megabases. So looking at cell line gDNA, and we're seeing, we looked at a total of 7 samples and a range from 3.7 up to 18.8 megabases. And we were able to call the 3.7 all the events up to 18.8. With sorted cell lines, we're looking at very much smaller events down to 1.19 all the way up to 100, and we're able to call 11 megabase event in this sample set. And TE biopsies and WGA, again, we're down around 8, and this is just an example here of a TE biopsy calling the 8 megabase event. So I think in Catherine's talk, she's going to introduce how you can utilize two workflows in your lab to balance the trade-off between sensitivity and specificity and calling smaller events. And this is just a summary of some of the smaller events that we looked at in the previous in these cell sorted experiments that we did with Kangpu Zhu's lab. There was a range of quite small samples that we investigated what was required to actually call down to 1.8 megabases, and it required increasing both the transition penalty and the tile size of the baseline to call these small events. So this is an example of what this sample looks like that had 2 events, a gain of 99 megabases and a small 1.8 loss here. So I'll just finish up with the mosaicism workflows that we've developed and how they're doing with the same with some experiments we did with Kangpu again. Again, this is a mixture of cells that were picked under a microscope. You have a normal male mixed with a female with a trisomy 21 gain, and then the cells. This is a 5-cell mixture, so it's the addition of 1, 2, 3, or 4, or 100% of the mutant cells. And you can see that with our mosaic workflow, and note actually that there's because you're mixing XX and XY, there's also mosaicism on the X and Y chromosomes too in these experiments, as shown here. So we're able to go from calling 20 all the way up to 100% mosaic mixtures from a 5-cell mixture. So to complete my talk, we have a robust aneuploidy detection workflow by Lowpass genome sequencing in the ReproSeq kits. It's rapid, flexible, and simple. And we've spent a considerable amount of effort in dialing in the software to improve its performance on a variety of samples, and with a focus on mosaicism detection, automatic mosaicism calling and detection, and calling of small events below 8 megabases. And if you want to hear more of the work that we did in collaboration with Kangpu, I have a poster that's it can be viewed in the poster viewing area. Thank you.